Thank you, Mike. Welcome everyone to the first talk. Is going to be given by Angela Yao, which is assistant professor in the School of Computing at the National University of Singapore, and she's an expert on activity recognition, image segmentation. He has got the NRF Fellowship for Artificial Intelligence, and has got many grants from industry. So it's a pleasure to have Angela here, and thank you for joining us to this EPIC edition.
Hi, Giovanni. Thank you for the kind introduction. Let me try to share my screen with you guys. Okay, so I think, can you guys see my screen?
Yeah, clearly.
Triple. Okay, so yeah, so I like to thank all the organizers and hosts of this workshop, and also thank them for inviting me to speak. And for our audience out there, I wish you all a good morning or midday or evening, depending on where you're joining from. So it's a real pleasure to speak with you today, so from Singapore, and also to present to you some of my group's work on video understanding, especially in egocentric video. So with that, I will jump right in. So yeah, the theme of this workshop is on egocentric perception. So I guess everyone in the audience is already aware that egocentric video, it offers a unique viewpoint, which is this first person look into people's daily lives and daily activities. But this perspective also adds a lot of new challenges also, which maybe require some slightly different considerations than what we would normally find in video understanding, standard video understanding in computer vision. And so amongst these different factors and considerations might be the fact that there's some variations in shape and appearance. So what we mean by this, if you have a look at these clips on the right-hand side here, comparing standard view from egocentric view, is that just the whole scene or the object or the actions, they look a bit different than what we're used to, right? And additionally, because this camera is mounted on the individual and moving with him or her, you definitely end up with a lot of movement or blur or motions, as well as occlusions, in the sense that things come in and out of the scene very quickly. The video sequences, as they're usually mounted with the individual as they go out throughout the day, they're taken as a continuous stream, right? So over longer durations of time. This is contrasted with the classic few second or maybe like 1 minute type of clips that you might extract from a YouTube video. And finally, because these videos are following people around throughout the whole day, we end up with quite a bit of footage. What we observe is of people interacting with objects in their surrounding environments. And for today's talk, I would really like to focus on these last 2 points here, and introduce some of the work from my group looking at how to specifically handle video understanding over these longer durations of continuous streams, as well as modeling hand-object interactions. And in our interest of looking at long streams of video, because this is what you might, as a common type of footage that you might get in egocentric footage, this comes to the first work that I would like to present, which is temporal aggregate representations for long-range video understanding. And here specifically, we're tackling this problem of anticipation. So this is where you observe some video sequence here, and then you want to predict what the person will do next, right? And for anticipation, there's actually a couple variants of the task, and to highlight 2 of them. One is this next action anticipation, where we want to predict just the semantic label of the action after some time point tau, or dense anticipation, which is some form of segmentation of the future, if you will, where we predict what's going to happen and also for how long into the future. And so in the context of all these different factors that we have to consider for egocentric footage, and especially also then for anticipation, some questions came up of this whole handling of the time. And I think these are also pertinent questions for many other video understanding tasks as a whole. So specifically, how should we model these temporal or sequential relationships, right? And with deep learning, what often happens is we end up building the temporal model directly into the network architecture itself. So this is some implicit modeling done via the an RNN or a temporal convolutional network or a transformer or so on. But if we do this, then this means also that the architecture tends to dictate the temporal extent, which can be modeled or accounted for due to either some computational or learning constraints. And so directly related to this then is we want to ask, well, what temporal extent of information and context should we be processing? And how far back in time do we need to consider, right? Additional questions include what temporal scale we should estimate these feature representations, and at what temporal scale we should derive these representations at. And then, should we be computing these features, for instance, from a single frame at a time, or maybe segments of like 16 frames, 32 frames, or even longer, right? And very closely related then to deriving these features and the temporal scaling that we should be deriving these features and representations is how much semantic abstraction should we actually derive from this representation? So is computing frame-wise or segment-wise features sufficient? Or maybe we need to actually explicitly detect the objects or people, or maybe even directly output the action labels for some of these segments that we've observed, right? So how much semantic abstraction do we really need? And so linked with this last point, obviously, is that the higher the abstraction level, the greater the computational demand, right? There is also the strong possibility that because we're relying on these other algorithms to extract the inputs, for instance, these action segment labels, then there might be errors. And because obviously segmenting these the previous inputs and estimating the labels is also a challenging task in itself and non-trivial. So any mistakes that we might make in this sense then ends up propagating downstream as well. So these were all of the many considerations and questions we had in mind when we were sitting down and trying to develop a new type of representation for looking at long range video. So long continuous streams of video, specifically in our aim for doing anticipation. And so keeping these things in mind then, I want to present to you what we came as, let's say, our solution to handling this. And specifically, what we were aiming for is to have flexibility in the frame input. So we wanted to be able to cover this whole range from very low level feature representations to higher level semantic labels. And then also have the ability to meaningfully integrate our recent observations with long range context, with explicit control and also done in a computationally efficient way. And so this is our interpretation of this. So what we're going to do is represent each frame here or segment input of the video, whatever the smallest input token might be, as a single color block. That's what we're showing here. And in anticipation, in this task, we're only observing these solid colored blocks of the sequence. And then in the part that goes into the so-called future, we don't know what we haven't actually observed them. So here I've actually colored these blocks according to the actions that they represent, that specific frame or segment. But in practice, we don't actually know what these are. So these small units simply represent the feature itself. And so the first design choice that we made then was to take this observed part of the video stream and partition it into snippets. So each bracket or brace here is representing a snippet. And these snippets are going to be the basis of our working units. And to represent this snippet, we make the simple choice simply to max pool the frame-wise features within these snippets. And then we end up concatenating everything together to represent this whole portion of the sequence. So when we are representing this whole, a fairly long extent of input, we're going to call this something called the spanning pass. Depending on the actual data set that we get, we've actually just end up using the entire sequence, whatever is given as the sequence itself. And then we want to pair this together then with observations that we have just made currently, right? So this is our so-called recent past. And we're going to represent the recent past in exactly the same way that we talked about the spanning past, but maybe with some slightly different windows, snippet sizes, and number of partitions, okay? So what do we do with these two types of features then? We have our spanning past and our recent past. What should we do? We're going to merge them in what we call this is a coupling block. So we merge these two together, and the coupling block consists internally of these two non-local blocks, which first applies self-attention to the spanning past itself to derive some intermediate feature. And then we're going to couple this with a second nonlinear block with respect to this recent feature, and merge these together to give us two additional outputs then. Again, so these are some attention reweighted representations of the spanning past and the recent past. And now, because we were faced with this question, well, what temporal scaling should the features be derived from? We decided to design these snippets over varying lengths to really cover different granularities of the time scale. So for the spanning past and the recent past, we end up with multi-granular representations of the sequence. And for each of these, then we're going to couple these in this coupling block, as we just mentioned before. So for each of these granularities, we have their own dedicated coupling block. And now this is where the real strength of our representation comes through, is this ensembling effect, where we create an ensemble of these coupling blocks over the multiple spanning scales to form what we call a temporal aggregate block, in which we merge together this attention reweighted outputs via some max and some linear operation. So here I'm just showing one such temporal aggregate block for this one recent scale with respect to all the different spanning scales. But we actually do this as an ensemble, so for each of these recent scales as well. So here is one, and here's another. So the overall model itself is this ensemble of the temporal aggregate blocks, which in itself is yet again an ensemble of these multiple coupling blocks over the multiple scales themselves from the spanning past. And these representations, they're fairly generic. So we simply merge the feature representations together. And then depending on how we want to design this final output architecture, we can actually adjust the feature representations for various video understanding tasks. And in this case, in our work here, we were focused on these two forms of anticipation. So we use simply a linear projection layer for the next action anticipation, or we plug it in as a context vector for an LSTM to do dense anticipation progressively. But what we can do is actually make some small changes over the range that we consider as the spanning past and recent past, and adapt this whole framework also for other tasks like action recognition, or recognition of the this complex activity recognition over the whole sequence, or also for segmentation. And so this model that I've shown is actually quite simple. It's essentially an ensemble model that leverages self-attention and cross-segment attention over multiple scales and temporal extents, but we find it to be actually quite effective. So at the time that it was published, we tested against state-of-the-art on various tasks that are applied to these slightly longer range videos. So from benchmarks that are typically used for action segmentation. So for example, breakfast actions, where you might have sequences in the order of about 10 minutes or so, right? And for tasks like dense anticipation, also the recognition, this complex activity recognition, so recognizing the overall goal or task as a whole 10-minute sequence, as well as action segmentation, we observed that our results are either comparable or better, but on par, let's say. And then on the hallmark tasks for the EPIC challenge of 2020, which were next action anticipation and also action recognition, we found that we did quite well with such an architecture. So we ranked first for action and next action anticipation, and second for action recognition. So this was just this first part on talking about how we can ensemble these features of different temporal extents and scales together, right? Next, I want to highlight a few of the interesting findings that we observed from ablations of this model, which I think give some insight to the overall understanding of how to do video understanding from long-range video sequences. So we did several ablations on breakfast actions and 50 salads. And the first thing that I want to highlight is about feature abstractions. If we start out with this weakest feature setting, so these would be the Fisher vectors here. Sorry, this already jumped ahead. The Fisher vectors here I think these are Fisher vector representations of improved dense trajectories. So these are not even deep features that we're talking about here. And if we look at some comparable work at the time, so this is from Yazan's paper on, I think this was, yeah, when will you do what? So this is one of the first anticipation papers in 2018. So these are the comparable work, and they're using the same features as us, but they perform segmentation first to get action labels before putting it into either an RNN or a CNN. And you can see from our results that we're roughly comparable, right? So on breakfast, we're just a little bit lower, whereas on 50 salads, we're marginally higher, right? So our results here is basically saying that even though we are using Fisher vectors directly as input, whereas they use segmentation results derived from the Fisher vectors, we can achieve comparable performance. But if we were to replace our these Fisher vectors of improved dense trajectories with the stronger I3D features, then we already get a nice 10% boost here, shown here. And additionally then, if we perform a segmentation first on, again, using the same architecture that we just described, and then apply the segmentation output, then we get an additional 3% boost. And merging these two gives us an additional 4% bump, right? And so we achieve the best results, unsurprisingly, when we use the ground truth action labels instead of these segmentation results as input. And so actually, there's a pretty large gap still, actually, so instead of using segmentation output, we use the ground truth action labels instead. There's still this 17% gap. This indicates to us that the quality of the segmentation really matters. And what we're taking away from all of these experiments is essentially that improvements with stronger, you can get improvements if you have stronger features. So when we transition from improved dense trajectories to I3D, we get improvements if we progressively improve the segmentation accuracy. And in general, this higher input abstraction, so if we compare from a feature to a segment label level, having this higher level of abstraction definitely helps, but this is only true if they are sufficiently accurate. So if we compare here, for instance, so I don't have the numbers here, but I think our segmentation results are slightly more accurate than the segmentation used as input here, then we can get progressively stronger results. And then, of course, when we move to the ground truth, then we do even better. A second interesting observation that we had was when we varied the past extent that we use for next action anticipation. So here I'm showing a plot of how long this spanning past is here's a plot for breakfast actions, and here's a plot for this for EPIC kitchens. And interestingly, what we see is here on breakfast, we see this nice trend that the longer of a pass that we incorporate, the better the accuracy on anticipation. But this is not true for EPIC, right? So on EPIC, the performance stays more or less flat, regardless of the type of feature representation that we're using as input. And so our interpretation on this behavior is that it's likely because there's very fine granularity in the labeling of EPIC, right? And also the median action duration is quite short, so it's only about 2 seconds or so. So over the course of, say, 30 seconds, or already we're observing 15 or 16 actions. And so it's quite difficult to link together the temporal relationships over so many of these actions. And secondly, because this data set is so rich in labels, I mean, we have about 2,500 action classes, right? But only 30,000 samples total, then our speculation is that maybe this model is not able to learn all the variance of the relationships over longer extents. So therefore, increasing the scope of the spanning pass beyond some value, like 5 or 6 seconds, maybe probably doesn't do too much. So our takeaway from here then is to say, well, you know, you can interpret this as both good news and bad news, in the sense that the good news is, for computational concerns, we don't need to process or retain too much of the past to help us. But this is only true under certain contexts and scenarios, depending on what it is that we're observing and the type of activities. So what I presented to you now then, this is our temporal aggregates work. It's a flexible multi-granular framework for computing generic video feature representations that are applicable to various video understanding tasks, such as anticipation, recognition, and segmentation. And what we've shown through this work is that one is actually max pooling is surprisingly effective as a way to represent video snippets. So I didn't go into detail on the experiments here, but it's a very simple choice that we made, but we found this to be surprisingly effective in collapsing together these feature representations over multiple frames. Secondly, using attention mechanisms, as we did with these non-local blocks, they can be applied successfully to relate the current observations with something in the long-range context as well. And really where the strength of the modeling comes in is through this ensembling over multiple scales and multiple extents. From the experimental side, I think takeaways that might be interesting, even if it has nothing to do with the architecture itself, our findings were that having higher levels of abstraction make for stronger inputs, but this is only true if they're sufficiently accurate, right? So we do need to take care and trade off this computational expense. Do we want to bother computing these intermediate abstractions based on semantics, for instance, by doing segmentation of our input first? But at the same time, because there's this trade-off of computational expense, we have to ensure that it's sufficiently accurate that it doesn't hurt our downstream results. And the second part is that extending this temporal context, it can be beneficial, but really depends on the label granularity. Okay, so I opened the talk with this slide here, where we describe some different aspects in which we and different factors of consideration that we need to take into account when we handle egocentric video. And then I presented to you our method on temporal aggregates, which handles long-range streams of video data. And next, what I would like to do is move on to this second point on hand-object interactions. And our motivation really comes from the fact that, as we see in a lot of this egocentric footage, we end up looking at the person interacting with objects as they go about their daily lives, right? And these actions, they can be quite fine-grained and are often defined by the object and the type of interaction itself. I mean, for example, in EPIC Kitchens, the action is simply composed from the noun and the verb together, right? So this dictates our interest, or primarily motivates our interest in looking at this hand-object interactions. And what we observe for objects in particular is that often these objects, they end up getting transformed in some way over the course of the action, either visually or physically. And so in this example that I'm showing of cutting an eggplant, for instance, we see at the beginning the appearance of the eggplant can be quite different. But then and it changes progressively as the person slices it into these rounds and then chops it up into cubes. And so our interest is to capture these visual changes over time. And we want to do it with some form of visual relation reasoning, right? And now, because object detectors and trackers, they've really improved a lot, a common strategy, not only that we wanted to take, but also has already been adapted previously, is to first localize these essential entities in the scene, and then recognize the actions based on the detections of the hand or the object, as well, or also tracks of these objects over time. And so one standard approach is basically to take these detections or these tracks, and then what we might do is take features from the output of CNN's last convolutional layer, so on, and then reason about the action with some structures like graphs or visual relations or interaction networks. And this is one type of entity-based reasoning. So, or object-based reasoning, you can think of it as another way. So I'm going to refer to this as an explicit type of object-based reasoning. And two good examples of this is from these space-time region graphs presented at ECCV18, and also the spatial temporal interaction networks. So I think this is slightly more recent from CVPR of 2020. So I would argue that these form one extreme of this visual relationing reasoning, where we do it on explicitly localized objects. And then on the other end of the extreme are these feature-based reasoning. This is where you have approaches like non-local blocks, or here's another one, this GLORE, which is graph-based global reasoning networks. These are methods that relate the localized features from one location to another in the feature map. So even our temporal aggregates can be considered a form of this feature-based reasoning in a way, if you will, except ours are not on a feature map spatially anymore. It's just on in time, right? We're only considering the temporal dimension. Anyway, looking at these two, what we end up with is I think these form two ends of a spectrum in a way, right? So the entity-based reasoning, it reasons only between the detections or the tracks. So one possible drawback is that maybe they might end up missing some cues from the background, or they're not able to reason between the entity and the scene itself unless you add some additional architectures to handle this. And then on the other extreme here, this feature-based reasoning, this unfortunately, because what we're doing is we're relating these features to each other exhaustively. This requires a combinatorially large number of operations. And we can't really guarantee that all of the relationships that we're learning then actually correspond to some sort of causal nature of the action itself, or related to causal entities. And by causal entities, I'm referring specifically, of course, to the hands and the objects. So what we end up learning maybe has to do with some biases with respect to the scenes or some other latencies in the data set. And so our motivation here then was to strike some sort of middle ground between the two. And this then motivates the work that I'm going to present next. And specifically, our aim was to really leverage the use of these detectors and trackers so we don't have to exhaustively relate features to each other. But at the same time, we didn't want to be limited to the high-level semantics. And our argument here was that if you only take your feature representations at the very end of the network, these very high-level semantics, it might end up absorbing these finer-grained appearance differences. And what I mean by this specifically is, for example, if we look at this cutting eggplant example, this whole eggplant looks very different from this half sliced versus these cubes of eggplants and so on. At the final layers of a CNN, they might, if we're very lucky, they might all be correctly identified as eggplant, Or maybe this sliced visualization of the sliced example might be confused with some other more commonly sliced objects, like maybe apples or pears or so on. But either way, it becomes very challenging then to really integrate these fine-grained appearance differences of the object itself. And a second example of this concept of absorbing these fine-grained appearance differences is here, for instance, if we're trying to uncover something, right? So here, the hand comes and removes the towel, which then uncovers the highlighter there, right? But if we don't model this transition properly, this whole sequence actually resembles very much like putting something next to the something else, right? And so in that regard, capturing the transition of these appearance changes over time becomes critical in understanding the action itself. And so our hypothesis here in this work was that we should leverage these mid-level features as one way to do so. And so in this way, we want to actually make use of the explicit position information that we get, for example, from detecting or tracking these objects, but at the same time, we want to do our reasoning at this mid-network feature level instead. And so the work in this second work that I want to present to you, we proposed a module for these regions of interest, so ROIs, associated with the detections. And we want to work specifically with these mid-level features. So what we're going to do is start off with these T frames. So usually maybe 8 or 16 or frames. And then we pass these through some CNN. So for example, a ResNet 50 or some other form of 3D CNN. And as I explained the rationale before, here we're interested in working only at the mid-level. So for instance, after the COM4 layer of ResNet 50. And then what we're going to do is plug in our module here for relation reasoning. Then do the transformation in place so that the features themselves can be continued to be processed throughout the network itself. And so accordingly then, because what we're doing is we're working on these regions of interest. And here we're essentially transforming them in some way. Before we allow it to be continued process, we name this module TROI. And this module actually is quite flexible in that it can be placed into different CNN backbones. So whether it's ResNet 50 or TSM, so we verify this with some other ablation experiments as well. And if we take a closer look at this relational reasoning that we're doing here at this mid-feature level, what we're doing is we're learning a mapping from the original COM4 feature map to some transformed feature map here. And what we do is we take these corresponding regions of interest based on the detectors outputs or the tracked outputs at each of the associated frames. We take them out, extract the features associated with them, and then pass it through. So we give it some sort of positional and temporal encoding associated with both the time and the location in the scene, and put them through this some transformer encoder here. And this transformer is what's doing the explicit visual relation reasoning over these regions of interest. And then based on the transformer output, these values, so these features, they get transformed in some way, but it's done, the transformation is still done in place, right? So they still end up exactly where they were originally, so that this entire feature map here is just slightly modified and can then progress onwards in the original CNN backbone. Now, in terms of the relational reasoning itself, we picked our transformer here, this encoder here, purely for performance reasons. So we also tried it out with using a graph convolutional network in the middle here. And this works as well, but through our experiments, we just found that the transformer had a slight edge performance-wise. So that's why we ended up using the transformer in the version that I'm showing here. And in terms of where to put in this module, we really found that the way that it's designed, actually it works well at this mid-feature level. If you go any earlier, for instance, after the Conv2 layer or so on, we find that these features are probably too low level to work with still, so the performance drops a bit. To do relational reasoning over these features levels are still too low level. And then any later, you actually, because these feature maps get progressively smaller and smaller, you lose the associated positional information that's associated with these regions of interest. So this, after this Conv4 layer, for instance, in a ResNet 50 is a nice trade-off between the two. If we look at performance, we tested on something V2, as well as EPIC 100. And if we start off with this experiment looking at just using the ground truth bounding boxes, and then we're comparing with this other work called STIN from CVPR 20, which is also using the ground truth, then we find that we actually significantly outperform these spatial temporal interaction networks by. So our work was state of the art at the time, at least for this given input of the ground truth bounding boxes. Unfortunately, so we do keep this performance advantage against competing methods if we use actual detections. But what was a bit disappointing was that there's still a bit of a drop in performance. So we lose about 3 to 4% if we go from the ground truth to the detection outputs. I mean, so in that sense, if we compare to other methods that are using the detection outputs instead, then the significant lead that we had previously is not so large anymore, right? And so this tells us that basically that the quality of the detection, it still matters. And so we need to basically safeguard, actively work in some kind of safeguard with respect to the robustness. If we want to do visual relation reasoning based on some detection or some tracked outputs, then we need to put in something to explicitly handle this robustness factor, because these detections or tracks are not going to be correct all the time. If we look at performance on a data set like EPIC 100, we're sitting in a similar range where we have just slightly higher performance than the baselines published previously at the time, so it's for slow fast and TSM. And so given that our action accuracy is on par with these two methods, we find, but our verb accuracy was actually much better, we think we're losing out a bit because of this noun accuracy here. And we can confirm this because if we merge our results from TSM, then we get quite a bit of a boost. So then we do even better on the action accuracy itself. So what is making us fail at this noun recognition then? So this leads us to take a closer look, where we tried to break down the classes where we found we were doing better, and then also we were doing worse than TSM. And what we found was that if we improve, that we end up improving over TSM on actions that involve small objects like spoon or knife, or these mid-sized objects like pan or bowl. But then when you end up with these very large objects, like what you see here, I think the way that the hand detector and object detector works for these release bounding boxes is that this is our speculation also, is that this detection algorithm has a very strong size prior. And so when it's localizing things like cupboard or fridge, it only encompasses the handle of these objects. And so we're speculating that in these cases, the region of interest for this interacting object, it doesn't give us enough visual context. And so one needs to localize the entire object or appliance to really identify the noun. So before we had hoped that this would be picked up by keeping our transformations in place and progressively still processing the entire scene in the CNN itself. But it seems like this effect is still not strong enough. So when these localizations are wrong, we tend to do quite poorly. Here are some other examples also where just this whole localized object is misleading in some way. So here we're dealing with scissors, but we actually localize the entire drawer. And similarly with the tap, the tap is over here. Or I mean, I guess you can argue that's the handle of the tap, but we only get the water that's coming out of the tap. And similarly on something V2, when we were using the tracking results what we find again is that there's these instances of these catastrophic tracker failures, where essentially there's no overlap between the ground truth and the actual detected results. So I think here green is the tracked results, and then the blue is the ground truth. And because the model is really trained to focus on paying attention to these regions, these failures definitely degrade the model. So if I summarize here, what I've shown here is this TROI. It's a plugin module for existing CNNs to do visual relation reasoning between hand and object interactions or localized entities, as I've written here, at this mid-network feature level. And so this is a new way, I think, of thinking about visual relation reasoning, is to work with these regions of interest at this mid-network feature level. And there's obvious benefits to modeling the hand and object interaction. So because we get this extra boost of semantic information at the same time without having to just, let's say, exhaustively relate all of these features at every single location to each other. And this, I think, is especially essential for egocentric video, where we are observing, a lot of the footage we are observing is exactly that. It seems, at least from our experimental results, that correct localization or robustness to these localization failures is still the key to success. And at the moment, there's still quite a gap between the ground truth and the tracked results, which suggests that, as a community working on these videos, I think we need to, one is improve our ability to do tracking in this egocentric video. And so I think when I saw the program, I think there is a presentation on this, so I'm looking forward to hearing about this as well. Then the other is, how can we then improve, the localization and the tracking, and also to endow in robustness to localization failures. So now I want to come to the last part of my presentation. And given this context that we've seen now, where we say, we want to model hand interaction with objects, but we're still struggling a bit with the tracking and the localization, this motivates the last part of my presentation. I'm really excited to present this to you guys because it's really hot off the annotation pipelines, I guess you could say. We're motivated by the development of a smart assistant, so some sort of situated AI assistant or agent, which maybe sits inside some smart glasses and communicates with the wearer as he or she is doing some complex task. And so AI assistants are actually slowly popping up in our everyday lives, whether it's following some recipe to cook, or when we assemble IKEA furniture, maybe when we rewire some short-circuit electric switch, all the way to training mechanics or surgeons or nurses for learning some new operating procedures and so on. And so egocentric vision, I think, is really well designed for this type of setting, where you have this task laid out in front of you, and you can now imagine you have the smart assistant can recognize what you're doing, anticipate what you're going to do next, but also provide you support at the time. Provide support live about what tools you might need, what parts you need to fetch, what actions you should take, maybe give you feedback, whether you've done something correctly. And these are exactly the tasks that myself and also my group were interested in going after as the next step for video understanding and action understanding. And so to help us do this, what we've done is we've designed this new task of toy assembly and disassembly. And so what we've done here, these are simply take apart and put together types of toys with, I think it ranges about 10 to 20, 30 components over a series of steps where we assemble these toys. And we're really interested in targeting this type of multi-step setting that you might find in instructional videos or cooking videos that span over longer periods of time. And we also want to work with these non-strict sequences, because this is where having this assistant becomes interesting, right? Where you might not even have to follow a rigid order of steps. And so if we look at this toy example, for instance, we might be, the toy can be assembled in varying orders, maybe starting first with the chassis or the arm or the wheel, and then we take them apart. When we take them apart again, we can actually pretty much be in anywhere. So of course, we're not the first to come up with such a task. There's plenty of data sets out there with similar criteria. One thing we found out, or rather the reviewers so very politely point out to us all the time, is that these data sets are too limited to the cooking or kitchen domain. But there are a few assembly data sets now as well. So two very nice examples, one of which will be presented at this workshop also is Mekano, and also this IKEA furniture assembly data set. And these are, I think, the precursors that also gave us inspiration for going after this toy assembly data set. We're following their footsteps in that we want to now scale up the number of items that we assemble and the number of subjects. In our unveiling here of this Toys 101, what we call, and this is a multi-view static combined with egocentric data set. So we have 8 static camera views mounted on a rig on top of a desk, and then also at the same time these 4 egocentric views that you see. So they're taken, so the person is wearing a customized headset with 4 cameras pointing at the corners of each of these. And then we're making these recordings while the person assembles and disassembles these take-apart toys. So to record this data set, we built up a desk-sized cage with this yellow piping that you see here, on which we mounted these 8 RGB cameras, and these are going to provide our static views, while the head mount has 4 monochrome cameras, one on each corner of the head mount there. And based on this setup, then we recorded. Oh, sorry. Let me try to play this. We record the person assembling and also disassembling the toy. In the end, we ended up with 362 sequences of people assembling and disassembling the toys. And from all the views combined, we have about 4,300 videos or 500 hours of footage, working on about 101 different toys. Right. We have 15 categories of vehicles, and we chose these toys specifically to have variation in the individual categories in terms of their color, size, and shape. And also what you can see is that the categories, they share unique and they have both unique and shared components. So for instance, in these 3 categories of construction vehicles here, they have these, so the whole body is the same, but the arm is just a little bit different, right? And then at the same time, we have some richness in the variety as well of the toys and vehicles. Let me speed up a bit here. I see I'm running a bit close to time here. So we defined actions on 2 granularities, fine level actions based on some interaction with only 1 or 2 single objects, starting with this pre-contact, where the hand approaches the object, and then the interaction itself, and then the post-contact. And at the coarse level, we string together multiple of these fine level actions that deal with only assembling 1 component into a coarse action. So here, this person is detaching the bumper. This consists of these 5 different fine level actions. And then when we're recording this data set, because we were interested in finding this problem setting where we want to tackle this temporal sequencing problem, which encapsulates the need to follow some loose ordering of steps, but still allow variation without being entirely random, we find that we indeed have this. So for different participants working with the same toy, they might assemble it and disassemble it in very different ways.
Angela, you have a couple of minutes.
Yeah. The other nice part here, what was really neat is that we actually have several instances where people make assembly mistakes and then they go back and correct themselves. And this I found super interesting also. So we're hoping that maybe this provides some opportunity for us to study this goal-oriented actions and so on. Let me wrap up. So I'll skip over the results. So these are some preliminary results. Our takeaway from these different feature sets that we use was basically that there's just this large domain gap between what we have in the existing benchmarks, which we see as a nice opportunity for study as well. And actually, our main motivation for using this desk rig, which you might think is pretty restrictive for an egocentric setting, is that we wanted to have these multi-static multi-views static multiviews to consider the 3D geometry of everything. So we already have the hand poses for all of the sequences, and what we're working on now is to try to scan all the toys to get the 3D geometry of them as well. And this starts to then merge video understanding and geometry as a whole. So let me conclude here then. So this is some first look at our large-scale data set where we're trying to bridge egocentric video understanding and the 3D geometry associated with hand-object interactions. We're targeting several vision tasks, so action recognition, detection, also this procedural or goal-oriented activity understanding, and then finally going after 3D hand pose and hand shape estimations, because this is one of my other areas that I work extensively in with these natural hand-object interactions. And what's upcoming now is to do object tracking with these constituent parts. So let me conclude then by thanking acknowledging my amazing crew of students and also collaborators. So the first two works that I presented, the first was published at Temporal Aggregates at ECCV. The second one on transformed ROIs is available on arXiv. And then this dataset collection is an effort now with some of these fine collaborators from Facebook Reality Labs. So with Robert and Daniel and Kun. And with that, then I would like to wrap up and thank you.
Thank you very much. Thank you. It was a very inspiring talk. We are out of time. Let's do just a couple of questions if someone have questions. I have one for you. Actually, thank you for mentioning Meccano, because my students were very happy when I suggested to play with toys. It's very inspiring work. And about streaming anticipation, about the anticipation of actions, do you think we need to look at the time complexity of our models? Because when we do anticipation, we should complete our inference before the action starts. Do you think we should include this sort of idea of a streaming anticipation where we have to consider ranking methods also considering the time they need to infer the action? Of course, there is still big gap without considering this, but if we want to have real systems which are able to anticipate, probably this is something we need to consider. What do you think about it?
Yeah, so I think you're absolutely right, Giovanni. This time complexity as an issue as a whole, I think this is something that we've, at least in terms of most of the work I've seen in anticipation so far, we've kind of neglected at the moment because we still study it as a very academic problem rather than, you know, what do I need to put this into a real system in this motivation of this smart assistant, right? So this has to do with the how much time it takes, but also the computational complexity, right? We assume that we have all these features extracted, pre-extracted and given to us as inputs. But when you're really working off of these headsets, these are very lightweight computational platforms, right? We don't have access to all of this to crunch all of the data for that we currently do. So this is definitely something that should be factored in. And I think we can definitely take a note from the folks working in some of these other, for instance, these enhancement tasks or other low-level tasks that have moved really onto mobile devices, mobile computing platforms as their test bed for the algorithms that they develop. At the moment, I think there's still a bit of a gap in our community still, where we're still really thinking about anticipation because it's a fairly new problem also. How do we think about this in a fairly academic way in the sense, you know, what is the right way to do the modeling and to think about how do I set up this problem and so on. So I think we'll get there. There's also as the field grows and there's expanded interest in also working with algorithms jointly with hardware, this will definitely come into play.
Great. There are a couple of questions. One is regarding the second work, does the scale of the ROI impact the decision on where to place the TROI model? And have you considered modeling interaction across different layers?
That second part is a very interesting point. Actually, we haven't. So that's a nice suggestion, which I think I'm going to take that as feedback. At the moment, what we do is we standardize the output. So for each detection, each region of interest within the feature map, when we take it out, we standardize it to a fixed size. So obviously, we do run into some issues if the objects are too small. By the time you get even to this COM4 layer, you're down to maybe only 2 by 2 pixel units within this COM4 layer. This can be problematic also, yeah.
Thanks. Next question is, TROI looks very exciting, of course. Is narration recorded as well as fine coarse actions?
We do have narrations, we just haven't processed them. So at the moment, I didn't include them in here because I can't really comment on the utility of the narrations. We definitely did record the narrations and we used them. So here I didn't show our whole annotation pipeline, but we were making use of these sometimes, especially looking for keywords, because these narrations were actually done live. I think this differs a little bit from the standard EPIC setup, right? Where you guys, if I understood correctly, you narrate afterwards, you watch it again and narrate afterwards. So these, we asked the participants to talk about what they're doing live while they're doing it, so that it's more or less in sync with what's happening. Okay, so thank you very much again. And we are going to